We're going to take a look here at example number 7. This will actually be our last example for this particular section. Again, our goal is to try to see how we can take all the ideas from this section and start to combine them to understand how to show that a vector field may or may not be conservative. So let's see. I want to show that this vector field is conservative. Now, if I wanted to do that, again, I can think about the two most recent theorems that I have available. I can again start by noting some of the same stuff I did in the last video. Specifically here, I can say that we see that f is defined on R2, right? Like, again, if I look at what values of x and y are allowed to be plugged in here, there doesn't seem to be any restrictions. I'm not going to ever divide by 0 or square root of negative, nothing like that. So I can also specify, like we did in the last video, that R2 is open and simply connected. I can also note that f, I'll say f's components will have continuous first order partials. So again, the two most recent theorems apply. The two most recent theorems apply. Well, then I can go ahead and actually start to quickly see, like I did in the last video, that if I was to take a look at the partial, remember, P is sitting here and Q is sitting here. So if I do partial of P with respect to Y, notice I'm going to get negative 4Y. And if I did the partial of Q with respect to X, I also get negative 4Y. So I know that the partial of P with respect to Y is equal to the partial of Q with respect to X. And by the most recent theorem, that actually tells me exactly what I need. Let's take a look at it. This theorem said, if you have a vector field, it's got to be on an open, simply connected region D. That was our R2. Then, as long as we had continuous first order partials, which we did, and these two things came out equal, which they did, then we know f is conservative. So f must be conservative. Remember, that means that I should be able to find a little f function so that its derivative, or sorry, that its gradient will be equal to this capital F. Now, I don't know about you, but that's a pretty intimidating thing to try to think about. If we had just started with show that this is conservative, and then I could have tried to hunt for a potential function, I might have hunted all day. What I know now is that a potential function is definitely out there. I was able to show without ever finding that potential function that one exists. Now in part B, I'm going to be asked to actually find that potential function. Okay, there is a way that I might be able to do this, even if I have a really complicated sort of function, like this capital F that's sitting here. So let me show you at least a quick technique for how I might do this. And example number 8 in the notes here, the next example will actually show you or give you the opportunity to practice that. So here's what we have. I'll start by saying we seek a function f of xy such that the gradient of f will be equal to capital F. So automatically we know a couple things. We need the partial derivative with respect to x of our function to come out to be what that p is, that 3x squared minus the 2y squared. And we also need that partial with respect to y to come out to be equal to what q is. So here's what I'm going to go ahead and do. I'm going to deal with very specifically that partial with respect to x and see what I can do with it. So we see that if I was to go ahead and integrate that partial with respect to x, specifically with respect to x, that would be finding an antiderivative of a 3x squared minus a 2y squared dx. Okay, so that is what I'm going to be looking for. And here then, I could easily see that I would propose then that f of xy, which is what I get from the left side here, would have to be equal to something like, get this out of the way, something like an x cubed minus a 2y squared times an x. But of course, don't forget at the back, plus a constant, right? I'd have to have some constant floating around at the back. But this constant doesn't necessarily just have to be numbers. It could really be any other sort of a function that involves y's, or just constants on their own. So I have something like this. Now, this is really powerful because this is telling me that whatever my function has to be has to look like this, and then some other stuff with just y's. But I know that if I take the derivative with respect to y, I do a partial of this with respect to y, I should get right back here to my negative 4xy plus 3. So I'm going to go ahead and start with that. So I'll say if we take this version of fxy and differentiate with respect to y, we get, well, let's see, if I took that and I took the derivative with respect to y, obviously the x cubed just completely disappears. I'm going to get a negative 4y squared, or sorry, negative 4yx, and then I'll get an h prime of y, right? Because that's got y's in it. But I know something. But we already know that the partial with respect to y was supposed to be equal to negative 4xy plus 3. Well, this means then that h prime of y has to then be equal to the value of 3. But of course, this implies that h of y has to be equal to 3y, but maybe plus just some constant. So if the constant can be anything, then we could really say that our f of xy could now be kind of updated. It could actually look like an x cubed minus a 2y squared x plus a 3y plus some sort of a constant. And if we pick that constant to be anything in the world, what we've seen is we've found a potential function. So this is a potential function for f. That's really, really powerful. So this sort of technique is able to be used not only in 2 dimensions, but also in 3 dimensions. And we'll see that at times, using this idea of understanding, again, if a vector field is conservative, is of so much importance, very specifically because if I go all the way back to the beginning of this lesson, the idea was there's an easy way to compute a line integral. And the only way you can use this is if you have a potential function. So knowing that a potential function exists, that is, knowing that my vector field is conservative, is so crucial to being able to quickly calculate problems involving line integrals. If I go all the way back down to this last part here, part C, suppose then that I was given a curve like this. R of t is given by this crazy equation, where t goes from 0 to pi. And I want to find the work done by f moving the particle along the curve C. Now, of course, I could start to set up my work integral like I've done in many of the previous sections, but I can start to see just how terrible this would be if I started to proceed by doing like an f dot dr, or doing a writing down like my f and plugging in my r, and then actually doing my r prime, and then doing my dt, like I can do it this way. That's totally possible. I could start doing this work, but just think about how terrible it's going to be to like first take the derivative of this. Think about how terrible it's going to be to like plug these formulas here for x and y into what this vector function actually is, or this vector field actually is. It's going to be horrific. I don't want to do that. So I might all of a sudden really hope that this is a conservative vector field. And we know that it is. So I can say this: since f is conservative, we showed that in part A, then we will plan to use the fundamental theorem of line integrals. We just need to figure out where this curve starts and stops. So we see that r of t starts at, well, let's see, what's r of 0? If I plug 0 in here, I might notice that I get 0, 1. And it stops when I plug in pi. And when I plug in pi, I get 0, negative e to the pi. So automatically, I can state this: by the fundamental theorem of line integrals, the integral of c, or across c, of f dot dr, I know is the same as saying the integral of the gradient of f that we defined up above. And I can just go ahead and say, why don't I just evaluate that function f at the stop point and subtract what happens at the start point? If I didn't have the potential function up above, if I couldn't find it, I would be stuck here because I wouldn't know what I'm plugging into. But because I have that function, this is easy. And again, since c can be anything, I'll often just select that constant to be 0. So notice here, if I was to go ahead and plug in 0 for x and e, or negative e to the pi for y, notice I'm going to get 0, 0, and negative 3 e to the pi. And then I'm going to plug in 0 for x and 1 for y, and that's going to be minus 3. And I'm done. This is the power of the ideas of this section, is that we can go ahead and understand how we can actually tie all of this together to really help in the computation of various line integrals. Well, this is the last video that I'm going to do for this particular section. Example number 8 is down here for you to actually try. If we had had class time, I would have let you try to work on this one on your own. It would have been trying to find the potential function for this vector field. And notice that the process there would actually be extremely similar to what we did here on part B. So I'll ask you to reference part B as you try to practice with that question. Of course, if you have questions in general on this section, by all means, please let me know, and I'd be happy to help.